So hello guys, welcome to my YouTube channel again, and today we will be discussing the LeetCode daily for today, and the question number is 45 and the question name is jump came to, and this is a very important question from interview perspectives. Basically this has many solutions and all the solutions are very important here. Okay, so I'll advise you to first go through the question yourself and try to code it, try to apply your logic, and if you are stuck or if you want to know some other approaches, then go through this video tutorial. So in the question it is simple. Basically you are given an array, and basically this, like, I have changed the nums to ARR for convenience. Okay, yes, so you will be given a array nums that will be of length n, and you are standing at this position. So I'll explain with an example. You are standing at this position and the basic goal is to reach the end position, and what this value signifies the jump that you can take. Like, in order to reach the end index, you can take some jumps. The jump is like, if you are standing initially, you will be standing here. So if you are standing here, then you can take a maximum jump of 2. So you can take a jump of 1, also you can take a jump of 2. If you are standing here, you can take a jump of 1, 2 and 3. Here jump of 1 is possible, jump of 1 is possible. So you just have to reach the end. So suppose here you take a jump of 2, so you will reach this position. Then you will take a jump of 1 to reach this position, and then again you take a jump of 1 to reach this position. This will take 3 steps. But suppose now you are here, you take a jump of just 1, so you reach this position, and then you take a jump of 3 to reach directly this index, so it will take 2 steps. So that is why the answer is 2. Basically you have to return the minimum number of jumps to reach the end index. Okay, so yes, this is it for the question basically, and the num size is 10 raised to the power 4, and yes, nums values are from 0 to 10 raised to the power 3. So this is it for the question. Now let us come to the solution. So basically, if we consider a brute force solution for this, then this question is all about choices. Basically, you are standing at a particular index and then you decide to take some steps. Okay, basically you are standing at a particular index and then you decide that yes, at that step, suppose at that particular index the maximum jump is given by the ARR. So the ARR of I is suppose 5. So that 5 will signify the maximum jump that you can take. So suppose that is 5. So you now you decide, you can either take a 1 jump, 2 jump, 3 jump, 4 jump, or a 5 jump. So that is on you. So take all the choices, take all the 5 choices, and whatever returns the minimum value, that you will return. So basically it is a recursive solution. So if you are at a particular index, then you decide to, then you have some choices and you take the choice with the most optimal, you take the most optimal choice basically. Okay, so let us code that recursive solution. From that recursive solution, that is the brute force solution, from that recursive solution we will memorize it to make it a DP solution. Okay, and then there exists a O of n solution, that is a greedy solution. So I will be discussing all the 2 solutions, basically all the 3 you can say. So first we take int num is equal to ARR dot size. Okay, and then we call the answer is equal to recursive solution. So suppose initially we are at index 0 and we have to, so this is just the state will be just the index initially at what index you are. Okay, and directly return that answer. So this recursive function will tell me that if I am a 0th index and I have to reach the n minus 1th index, then how many jumps will I have to take. Okay, so int recursive, so this first takes at what index I am, so index I, then num, this is the size of the array and size of the vector, pass it by reference, otherwise it will make copies. So now you are at the ith index. Okay, so int answer is equal to, we'll initialize it with some maximum number. So let us take one maximum number, mx equal to 10 to the power 9. You can write like this here, 1 2 3 4 5 6 7 8 9. So this 10 raised to power 9 will signify that we haven't reached that position. So this is a very huge number. Okay, this is a huge number, and this signifies that we haven't reached the end. Okay, so here also if you return some huge number, like if answer is equal to 10 raised to the power 9, let us make it a max only. Mx is the max. Okay, so this is some kind of infinity which we are storing, mx or infinity only. Let us name it infinity. So if answer is equal to infinity, that means that you haven't reached the end. So return a -1, because in the question it is stated, okay, -1 is not the case. Okay, so then you do not need all this. But in some question there may be a case that suppose you are standing at this position and there is a value 0 here. So 0 will signify that you cannot take any step from here. Okay, so then you have to handle that case, but here it is guaranteed that you can reach the nums of n-1. So yes, so now you are at the ith index. Now you can decide whether to take a jump of 1 or 2 or 3 depending on the value of ARR of I. Okay, this is the maximum jump that you can take, max jump. So suppose if you are at an index equal to 2 and the ARR of I is suppose 3, so you can take a jump to reach. So from you can take a jump of 1, you can take a jump of 2, you can take a jump of 3. So if you take a jump of 1, then you will reach 2 plus 1, that is 3. If you take a jump of 2, you can reach, because you are standing at the 2th position, right? So you are standing at 2th position and you take a jump of 2, so you reach 4. You are standing at the 2th position, you take a jump of 3, you reach 5. So you just iterate over all these positions, and like for int j is equal to I plus 1, because the jump will start from 1, I plus 1, and j less than equal to I plus ARR of I. So this is the maximum position that you can reach, and this is the minimum position. Okay, and then j plus plus, but please ensure that this is out, this can go out of bounds. Basically you have to reach the maximum index is n-1. Okay, num -1. So basically you minimize this with n-1, num -1. You minimize this with n-1. Okay, so here suppose you are standing at the second last index and ARR of I is 10. So then you reach out of bounds, so we minimize it with n-1. So yes, so answer is equal to minimum of, because we call the recursive function for that j, num and ARR. This is the recursive function that we call, and since we have taken one step to reach that position, so 1 plus this recursive of j will tell me the minimum number of jumps required from j to num-1. But from I to j I have taken one step, so this one is from making a jump from I to j, and then this will tell me from j to n-1 what is the minimum. So this is basically recursion, like recursion will tell you from j to that, and since we have taken one jump from I to j, so that is why we add a 1 here, and we minimize the answer, and then we return the answer. Okay, so yes, and the base case is if we have reached the end, so if I is equal to num-1, then you directly return a 0. So since we have reached the end position, we directly return a 0. So yes, this is the recursive solution. Basically we take some choices, and depending on whichever choice is the minimum, we return that thing. But yes, this is not like the complexity is basically exponential, because at every position you are taking maximum of n choices. So okay, so what is, like, this is exponential basically. If in recursion tree, if you make the recursion tree of this, suppose there are just we have done some problem like Fibonacci and all. Okay, so there at every step we had two choices, whether to go to we had two choices, go to n-1 also and n-2 also. So that time complexity is 2 raised to the power n. Okay, because there were two choices, and at n stages we make the two choices, so it was 2 to the power n. Here we have how many choices? At max we can take a jump of num, and from num steps we have to take a jump. Okay, so we are calling from num, so it is nothing but n to the power n. So the complexity is very huge, and basically if I try to submit, it will definitely give me a TLE. Yes, so it is time limit exceeded. See, in such a small case, it is giving time limit exceeded. Okay, and just 73 out of 109 test cases pass. Okay, so this is the recursive solution, completely brute force solution and like recursive solution. But yes, see, now we come to how to optimize on this recursive solution. So how to optimize on this? Basically, we know that our state is defined by this number I, and then we will be calling for this I again and again. So there is overlapping sub problems here. And so what we can do, we can apply dynamic programming here, and we can memorize this recursive solution. So how to memorize this recursive solution? Basically, you can say that, see, as the only variable, like how to find the state of DP, like how to find the dimension of DP, the number of parameters which are changing, that defines the state. So here just I is changing. Every time I am sending this num and ARR. So num and ARR remains the same, and only thing, this J is changing. So we will make a 1D DP table. So vector int DP num size, and initialize it with -1, and then there is a, then we pass this DP in the recursive calls. Okay, vector int ampersand DP. So this is fixed, like if DP of I is already calculated, then I return DP of I, and here before returning, store it. Yes, so this is what you have to do, like how to memorize a recursive solution. This is same for all the questions. Okay, we haven't passed the DP here, so let us pass the DP here also. Yes, so now the time complexity is nothing but like yes, let us see first it is working or not. Yes, so it is passed basically. And now if I consider the time complexity, the time complexity is basically the state of DP. So if you want to find the time complexity of DP, then what you have to do is you have to find first the dimension of the DP. So dimension of DP multiplied by the transition time. So the dimension of DP is nothing but n, like num, or you can say the size of the array, and the transition time, this is known as the transition time. So in the transition time we are running a loop of the jumps, like the I plus ARR of I. So this is the number of jumps that you can take at every step. So maximum you can take a jump of n. So if you consider that maximum you can take a jump of size n, so the transition time is also n. So this is nothing but n square time. So the time complexity of this solution, this DP solution, is O of n square, and the space, since you are using a 1D space of this recursion, so the space complexity you can consider that as space complexity is O of n. Okay, so the space complexity is O of n and the time complexity is O of n square for this solution. You can also write a iterative solution. It is also very simple. Okay, if you want, I can give you the code of that iterative solution. So, and like if you don't understand, you can, like, basically how to go from recursive to the iterative. So whatever is the base case here, try to start from that state, and then the transitions will be similar. Instead of just the recursive calls, just convert this recursive call to DP of j. Okay, and rest of the things remain same. So yes, and let me also show you that solution, that recursive solution, that iterative solution. So for that iterative solution, see what I have done is this num is the size of the array. Yes, for this iterative solution, basically So I have initialized the DP with mx. Mx will signify that that state is not possible. So basically, because we were to store the minimum number of jumps, okay, so I initialize it with a very huge value. So this is the DP table. So the dimension of the DP table in recursive and in iterative remains the same. So after that, DP of n minus 1. So basically in iterative solution we start from the base case. So in the base case in recursion we wrote that if I am at the n minus 1 index, like num minus 1 index, then I do not need to make any jump, right? So DP of n minus 1 will be just 0. So that means that I do not have to make any jump from that position. And then since in recursion we were moving from 0 to 0 to forward, right? So that thing is opposite in terms of iterative. So in recursion, if I can show you the recursion one, so we were starting from 0 and we were going ahead. So this j is greater than this I, right? So we were moving from 0 to n minus 1 towards the base case, but in basically in iteration, in an iterative solution, we move from like the base case and then we go to the starting, right? So DP of n minus 1 is 0 and the I will basically start from n minus 2 because we already know this n minus 1. So that is why, yeah, just a second. Yes, so basically we already know for this n minus 1 what is the solution. We already know for this n minus 1 it is 0. So I will start from n minus 2, I greater than equal to 0, I minus minus, and then this transition remains the same. So this transition is same for both the iterative and the recursive solution. So j starts from I plus 1, j is less than equal to minimum of I plus con num minus 1. So in the recursive solution also this is same. And then DP of I, instead of calling, we directly minimize the DP of I. So DP of I is equal to minimum of DP of I comma 1 plus DP of j. So here we were making a call of recursive of j, but here we are doing DP of a. Instead of that recursive call, we have just wrote the value DP. And yes, so this is not unnecessary basically, because in the question it is given that it is always valid. But if in some other question you are given that it may be possible that you are not able to reach the last index, then you have to write like this, that if DP of 0 is equal to maximum is how I initialize it. So since it is not updated, that means that DP of 0 will store the answer, because in recursion we called for the recursion of 0. Okay, so DP of 0 will store whether DP of 0 will store. So here DP signifies that DP of I signifies that the number of steps, minimum number of steps you reach to you want, like you have to use to reach from the ith index to the n minus 1th index. So in the question we were asked to go from 0 to n minus 1. So DP of 0 will signify that the number of steps to go from 0 to n minus 1, right? So that is why the answer is nothing but DP of 0. So here you can directly return DP of 0 and this is also fine. So this is basically the iterative solution for this, but still the time complexity of the iterative solution is also n square and the space complexity is also O of n. But iterative is something better because it is not using the recursion, and recursion uses some extra stack space, but that is more or less the same. Basically the time complexity is n square and the space is n in both the recursive and the iterative solution. So this is first approach. So first we have seen the complete recursive solution, that is exponential time complexity, and we got time limit exceeded. Then we have seen how we can memorize this and reduce the time complexity to n square and the space complexity to O of n. We have also seen an iterative solution, how to convert that recursive code to an iterative code. But this is not it for this. Basically there is one more greedy solution, and let me tell you that greedy solution. Okay, so let me remove this, let me reset this, and as I said, I have changed this to ARR. Okay, yes, so now for this greedy solution, basically for this greedy solution I have this example, and through this example I'll explain what is happening. So this is basically telling you the index at which you are there. Okay, so this is telling you the index So the indexing is 0, 1, 2, 3, 4, 5, 6, 7, 8, and this is a 9 size array, and you have to reach the position number 8, and you are initially standing at the position number 0. So this box represents that the current state where you are standing, and the array is like 3 2 3 1 2 2 4 0 3. So if you are standing at this position, then you can take a maximum of 3 steps. If you are standing at this position, you can take a maximum of 2 steps, 3 steps, 1 step, 2 2 4 0 3. Okay, so now what we will do is, since I am standing at this 0 position and I have a jump size of 3, so from this 0 I can reach this 1, I can reach this 2, and I can also reach this 3. So basically these 3 numbers are in my window, like these 3 things are reachable from me. So this is my current position, and in the code I will say that this is the I. Okay, I signifies that what is your current position. So this is my I, like initially I is 0, and from this I can reach from I plus 1 to I plus whatever the value of this is, so I plus 3. So from this I can reach all the 3 positions. So what I'll do is, I will not take a jump from this to this or this or this. So I will not take all the 3 jumps, but I'll directly figure out which jump to take using a greedy solution. So I'm claiming that, like, what I'll do is, since we want to reach this end index as soon as possible, so what I'll do here is, I'll take a jump and I'll move to that particular index. That will, like, after reaching that index, after that I will be able to reach the most closest to this n minus 1, the farthest basically. So I'll take a jump to that particular index. From that I will reach the farthest. So see, if I take a jump from this 0 to 1, okay, in one jump I can reach from this 0, all the 3 are reachable. But suppose I take a jump from the 0 to the 1, so if I am at this particular index and suppose I take a jump, then maximum I can reach, because this value is 2, so maximum I can reach 1 plus 2. So 1 plus 2, because at this position I can take a jump of 2, so I can maximum from this I can reach I plus ARR of I. So 1 plus 2, that is nothing but 3. So I can maximum reach this 3. Okay, so if I take a jump from this 0 to 1, maximum to maximum I can go to this 3. After taking a jump and after standing at this 1 position, I can maximum go to the 3. Now suppose if I take a jump from this 0 to this 2, so this 2 is having a value of 3. So maximum to maximum I can reach a value 5, because this, if I stand at this 2 position, I can take a jump of maximum 3. So I can take a jump of 1 also, 2 also, 3 also. But if I take the maximum jump, so it will be 2 plus 3, that is I will be able to reach this 5 position. So this is 5. Then from this place, suppose if I take a jump to this 3rd index, then maximum to maximum I can go to this 4, because 3 is that position, and from 3 I can take a jump of 1. So 3 plus 1 is 4. So if I go to this 1 position, I can reach to this 3. If I go to this 2 position, I can reach to this 5. If I take a jump from this 0 to 3, I can reach to this 4. So out of this, whatever is the maximum is this 5, right? Whatever is the maximum, so at that index I'll take a jump. So from this 0 I'll take a jump to this 2, because after reaching this 2 has a maximum reachability. Okay, from this, because see, if I go to this 1, this has a reachability of just to this 3. Then this 2, if I go to this, has a reachability of this 5. If I go to this 3 has a reachability of just this. So all these intervals, if you consider the interval of this 2, all the other intervals are basically a part of this. So if you consider the interval of this 3, the interval of this 3 is nothing but 3 and 4. but the interval of 2 is way bigger than this, and it is enclosing this one also. So that is why we take this greedy step. We take a greedy step and move to that particular and take the jump to that particular index from which we can get to the maximum. Okay, so I'll take a jump. So I'll take a jump to this 2, and yes, so this is my first jump going from this 0 to this 2. So now I'm standing at the 2th position. So now I'll do the same thing. From the 2 position, I can either take a jump of 1, or I can take a jump of 2, or I can take a jump of 3. So now where to take a jump? So that again will depend on from that position what is the maximum reachability. So the reachability of this is this. If you take a jump to this 3, so it is 3 plus 1 4. If you take a jump to this 4, the maximum reachability is 4 plus 2 6. And if you take a jump of from this to this, the maximum reachability is 5 plus 2, that is nothing but 7. So what is the maximum? This 7 is the maximum. So since 7 is the maximum, then so you will take a jump from this position to this. So now you have reached this 5. So now if you have reached this 5, okay, now you have reached this 5. So from this 5 you can reach to the 7. So now you can decide whether to take this or take this. So from this you can reach 6 plus 4. 6 plus 4 is 10, but 10 is outside the loop. So you do not make this 10, you make this at 8, because num minus 1 is the boundary. So from this position you can go to 8 only. Okay, and suppose this is 0. Here 0 is not given, but okay, 0 is not given because okay, 0 can be given. Okay, sure. So here 0 is a possibility. So from the 7 plus 0, 7. So what is the maximum? The maximum is 8. So the maximum is 8. So basically you go from this 5, you take a step 1 to reach this 6, and from this 6 you will go to directly to this 8. Okay, from this 6 you will directly go to this 8. So how many steps? 1, you directly go 1 you reach this, then from this you reach this. So 2 jumps, then this 3 jump, and this 4 jump. So here the answer is 4. So in 4 jumps you reach this end. And basically suppose there is a clash. So here 4, 6 and 7. 4, 6 and 7. So basically you take, suppose there is a 4, 6 and 6. So 4, 6 and 6. So basically 4, 6 and 6. So it is better to go to this particular 6. Okay, the farthest basically. So if this is able to reach this 6 and this also is able to reach this 6, so it is better to go here. Okay, so if there is a clash, go to the maximum index, and okay, and whatever is the maximum you go to that. So this is basically it. This is the greedy solution. Basically we are trying to go to the farthest every time, and if I have to decide at which index to take the next jump, you find the maximum reachability from that index and go to that particular index which has the maximum reachability. So okay, so if I write the code for this, so int num is equal to arr dot size, and then initially this I is signifying at which position I am standing, and this answer is signifying at which, what is the number of jumps that I have to take. So while true. Okay, so this is the basic way, like I code basically. This is a not simple for loop. Okay, this is not a simple for loop, so it is better to code it in while loop. So initially you are standing at this position I. Okay, so you now from this I you can reach from I plus 1 to I plus arr of I. So these are the positions that you can reach. So what you will do, where you have to take a jump, the one which is having a maximum value of reachability, maximum value of reach, and reach is given by suppose reach is given by this I plus arr of I. Okay, so reach is given by I plus arr of I. This is the reach. I plus arr of here j plus arr of j. basically j is the position at which you are standing, and from that you can take a maximum jump of this. So that is the reach basically. So int mx will store the maximum reach, initialize it with 0, and mx index will tell me which particular index is giving that maximum reach. Okay, so for int j is equal to I plus 1, j less than equal to minimum, because we cannot go out of bounds, so we have to minimize it with n minus 1. So I plus arr of I and j plus plus. Okay, so here we are just checking which one is having the maximum reach. So if can reach, so can reach is equal to j plus arr of j, and here also we minimize it with n minus 1 because we cannot go out of bounds. Okay, so this is the maximum reach basically, min of the two. So if mx is less than or equal to can reach, so you initialize, you update the maximum to can reach, and you also store the index which is giving the maximum reach. So this is j. Okay, and then you directly change the I to the one which is giving the maximum reach, so index, and you update the answer. And if you have reached the ending position, so if I is equal to n minus 1, then you break. Okay, so and then after that you return the answer. So basically whatever I have told you here in this question, in this example, that is what exactly I have done. Okay, so I am checking which index is giving me the maximum reach, and I am directly moving my I to the one which is giving me the maximum reach, and I am increasing my jump, and if I have reached the last index, then I'll directly break. Okay, so let me test this. Test cases are passing. Okay, for this 0 we are getting wrong answer. So if there is a size of 0, then you can directly, if num is equal to 1, then you can directly return 0, because we are standing at the ending index only, so then we don't have to take any jump. So this is one edge case that you have to consider, and yes, it is working. Okay, so basically what is the time complexity? So space, we are not using anything here. So the space, in terms of space, it is O of 1 in space, and in terms of time, we are just O of n. So if you look at the example, every index we are traveling just once. So we are moving from here to here, or 2 times basically you can consider. So 1 time by checking, and again if we are reaching this position, then we are again moving it, but we are not iterating over every index more than twice. Okay, so here while checking, I am coming at this index, and suppose I go to that particular index, so again I have reached this, and then I'll move forward only, I will not move backward. So every index is being traversed just 2 times, so it is O of 2n, and O of 2n is nothing but O of n. Yes, so this is the most optimized solution, O of 1 in space and O of n in terms of time. Okay, so basically this is it for this question, and I have discussed 4 solutions for this, from the recursive exponential to O of n. Okay, so please like the video and subscribe to my channel, and if you have any queries, you can feel free to ask in the comment section. And yes, that's it for today, and see ya.